Okay, the exam timer is literally ticking down. You're staring at a 4-mark ray diagram in your Cambridge IGCSE physics paper. You probably think, hey, easy question, right? But you're actually hovering right over the single most common mistake that absolutely tanks top grades. Don't panic though, we are not about to rewrite your entire revision strategy today. Instead, we're going to make the smallest possible change for the absolute biggest mark impact.
Let's just dive right into it. Are you constantly losing marks on what should be simple reflection questions? Look, it happens all the time, even to incredibly smart students. Under the pressure of that exam hall, your brain just naturally rushes. You see a mirror surface, you see a light ray coming in, and you just quickly draw a line. But that rushed, panicked geometry, that is a painful, common mistake, and it instantly costs you those easy, foundational marks on light and reflection questions.
Because here's the brutally frustrating reality. One wrongly drawn line can literally cost you a whole grade boundary. And honestly, this is exactly why just passively reading a textbook totally fails. You can sit in your room and memorize the laws of reflection all day long. But if you don't physically practice translating that math onto the page correctly, the examiner just cannot give you the marks. The stakes are instant. You really cannot afford to lose your hard-earned grade over a simple geometric oversight.
Now, when you're looking at a standard setup, like the one we've got here, notice that dashed line right in the middle. You'll see the angles labeled I for incidence and R for reflection. Light rays change direction, right? And the very first quick win to secure your marks is understanding that we have to measure this amount of turn correctly. Think about it the way it's described in the physics principles. Imagine you are facing along the original ray in its direction of travel. Now think about how much your body actually has to turn to be able to travel along the new line. In math, that specific amount of turn is our angle.
So the crucial point here is establishing exactly what we are measuring against. We need a baseline. And in physics, that baseline is called the normal. It's defined super clearly. The normal is an imaginary line that is perpendicular, meaning exactly at 90 degrees or a right angle, to the surface right where the ray strikes it. You absolutely need a protractor to determine this precise degree of turn. Trying to freehand this is basically a fast track to losing marks, no matter how good you think your internal spirit level is.
Let's zoom out for a second and look at the broader examiner warnings. Every single year, students bleed marks for these exact same errors: missing units, rounding too early in calculations, giving super vague explanations, using the wrong variables, or making conclusions that simply aren't supported by the data. I literally cannot stress enough how easily these quick, sloppy mistakes can completely tank an otherwise well-intentioned answer. I mean, if you calculate the perfect angle but forget the degree symbol, you lose the mark. It's that brutal.
And this brings us to a massive turning point in your exam strategy. In just a moment, I'm going to show you the hidden examiner clue in the command words that completely changes your answer. Seriously, it's a game changer. But first, you need the foundational framework that makes that clue blindingly obvious. Because if you skip this framework, that clue won't help you at all. Okay, here is your blueprint. This is the main structured framework you need to consistently build top-band, exam-safe answers for literally any calculation or practical question in Physics 0625. Step 1. State the concept. Step 2. Provide your evidence or data. Step 3. Apply your scientific reasoning. And Step 4, which is absolutely the most critical, fulfill the command words using precise examiner wording. This 4-step sequence proves to the examiner that you aren't just guessing, you are systematically applying real physics principles.
So, how do we apply that blueprint to the actual math of a ray diagram? First, you've got to clearly identify the boundary between the two surfaces where the light ray actually changes. Next, you have to know the convention for placing arrows on your diagrams. Remember, a line without an arrow is just a line, it's not a light ray. Then, accurately draw that normal line we talked about, perfectly perpendicular to the surface. And finally, properly use your protractor to measure and draw those angles.
You can easily spot the difference between a failing grade and a top mark when you see them side by side. Take a look at the flawed, rushed answer. They measured the angle straight from the mirror's surface instead of the normal, and they completely forgot to include their units. Now look at the top band answer. They correctly used the normal line as their 0 point, they utilized the correct physics terminology, and they locked in the marks by fulfilling exactly what the command words asked for.
All right, let's do a quick challenge. Put on your strict Cambridge examiner hat for a second. Try to spot the error here. Where exactly did this student lose their mark when they were trying to measure the angle of reflection? Look really closely at where that angle arc is actually drawn.
Did you catch it? Here is the examiner-style correction, taking us right back to our trusty rules. The absolute golden rule here: always measure the turn from the normal, never the whole turn, and never, ever from the boundary itself. Just as the physics principles explicitly warn us, when you're measuring an angle turned by a light ray, you don't measure the entire turn. You only measure the amount of turn from that imaginary perpendicular line, the normal. Measuring from the flat surface of the mirror is literally the deadliest, most frequent trap students fall into.
Before you even think about turning the page in the exam hall, you've got to run a rapid final check. Did you verify your units? Are your significant figures appropriate for the data they gave you? And maybe most importantly, does your answer pass a basic reasonableness check? I mean, if you are drawing a reflection, your angle of incidence should visually look equal to your angle of reflection. If one looks massive and the other is tiny, you instantly know you've either misread your protractor or you're contorting your neck the wrong way to look at it. Solidifying this high mark strategy ensures those points are absolutely locked in.
Okay, so we've got standard reflection completely locked down. But what happens when a light ray is traveling from a denser medium to a less dense medium, and the angle increases so much that it exceeds the critical limit? At that point, the light simply cannot refract anymore. It gets completely trapped inside. This is the phenomenon of total internal reflection. And if you miss how to calculate this next crucial concept, it will severely eat into your exam clock when it inevitably catches you off guard.
You absolutely need to master this time control system to avoid the deadliest examiner traps. The next high-impact change is waiting for you, and honestly, it's a mandatory next step to secure your grade. Subscribe to our YouTube channel Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click on the next explainer right now to master total internal reflection, because you need to know exactly what happens to light when it can no longer escape. See you there.